In this video, we'll be discussing the phenomenon of stacking. This video takes the point of geometric stacking from Ronald's video and explained it in more detail with some additional graphics to make it easier to understand. For the purpose of this video, we'll be looking at stacking from a geometric point of view. i.e., we're going to answer the question, what causes the draw weight of a bow to start to increase so quickly from a geometric perspective? There's a couple of math tools that we'll need to use for this video, so we'll go over them quickly. When a force acts on an object at an angle theta, we can split that force up into x and y components and sum each component separately. Component of a force A is given by A times the cosine of theta. The y component of the force A is given by A times sine of theta. If the sum of forces is non-zero in a direction, then the object is moving in that direction. Sine of theta, as theta increases from 0 to 90 degrees, it increases from 0 to 1. From there, it decreases back down again to 0. Cosine of theta, as theta increases from 0 to 90 degrees, it goes from 1 to 0. An idealized spring creates a force proportional to distance that the spring has been displaced. Alright, let's start this explanation off with some definitions and assumptions. I'll highlight them as we go along. 1. The bow is a simple longbow that bends through the center, which we'll call point O2. The bow acts as an idealized simple spring. The unbraced tip of the bow is point A, and the tip of the bow is point B. The distance that the idealized spring is moved is distance AB. 3. The string angle is the angle between the bow string and the tip of the bow lip. This angle is called theta. 4. The string does not stretch. 5. We're pulling it back at exactly 1/2 of the bowstring's length. The draw force is Fd. 6. The angle theta is 1/2 of the angle at the point where you're drawing back. 7. The distance AB grows at most at the same rate as x. Now that we have the assumptions out of the way, we can start on the actual math. We'll start this off by looking at the tip of the bow. When you pull the bow back, the bow acts as an ideal spring, exerting force perpendicular to the end of the bow tip. Let's call this force Ft, or force at the tip. The formula for an idealized spring's force is F is equal to K times the spring's displacement. In our case, the displacement in the formula is the distance between the unbraced tip of the bow A and the tip of the bow B. From our assumptions, AB grows slower than the draw length, so we can treat Ft as being approximately equal to K times the draw length. Next, let's look at the bow string. When the bow is pulled back, there's a force exerted along the string. Let's call this force Fs, or force along the string. Note now that this force is applied at the angle theta to the bow tip. With these two forces defined, we can now take a look at the whole of the bow tip To make it a little bit easier to understand, let's rotate this image. We have that the bow tip is moving, so we know that the sum of the forces at the tip is non-zero. Looking at our diagram of the bow tip, we see that there's only two forces acting on it. In order for the bow tip to move, Fs must be greater than Ft, as the bow tip moves both back and down. Looking at the forces on this bow tip, we see that the component of Fs along the direction of Ft must be equal in magnitude, but opposite in direction. Then we can say that the y component of the force along the string is equal to the force at the tip. Zooming back out, we know that the force at the tip is such that it is approximately equal to k times the draw length x. So now we can do a little bit of algebra. If the force at the tip is equal to k times distance ab, well, we know that the force at the tip is equal to the y component of the force along the string is equal to k times the distance ab divided by sine of theta. Now, the final step. Note that we had that the force along the string has a y component equal to the force along the tip, but that we didn't say anything about its x component, which to draw force Fd has to take the whole of. One thing that I didn't mention earlier is that there's actually two forces along the string. There's one upper force and one lower force. Their y components sum to 0, as the point at which we're drawing back is only moving straight back, and we're left with just the x component, two of the x components. So we get that the draw force is equal to 2 times the x component of the string force. But we know that the string force is equal to k times the distance ab divided by the sine of theta. Now we can look at how these equations tie together. We can ignore the 2 times k times the distance ab term, as that part is roughly linear with regards to x, so it doesn't affect our final result much. Instead, we'll turn our attention to the cosine of beta and the sine of theta by taking a look at what beta and theta are. Let's start with beta. At the beginning of the draw, beta is 90 degrees, and throughout the draw, it decreases. With theta, we see that theta starts quite small and increases throughout the draw. Eventually, it gets past 90 degrees and keeps increasing as we continue to draw the bow back. Now the question is, what happens to the cosine of beta and the sine of theta as the draw length increases? We see that cosine of beta actually increases throughout, going from 0 to being almost 1 as we get closer and closer to 0 degrees. Now we move on to the final piece of the puzzle, sine of theta. At first, sine of theta increases, but as theta passes 90 degrees, it starts to decrease instead, getting smaller and smaller, but staying above 0. So now what do we have? We have a positive value that's getting bigger, divided by a value that's getting smaller. When we divide a number by something much smaller than it, we get a really big number. In our case, as the draw length increases, we're dividing by a smaller and smaller number, giving that the draw force Fd has to increase faster and faster. Now you might be thinking, well, longbows don't have siyas, so this math can't apply to Asiatic bows. And you'd be partially right. The behavior of siyas makes the initial behavior of the bow a little bit different. But once the string lifts off the siyas, we can see that the angles that applied to a longbow still apply. Then that means that the math still applies. And so too does the formula above. And there we have it, stacking as explained from a geometric perspective. If you stuck with me for this long, thank you for watching. I hope that you learned something.